So let's begin. Welcome Daniel Robertz from Plymouth. So he'll present on how difference equations appear in PDE systems and algorithms.
Thank you very much. Thank you for the introduction and thank you for the kind invitation and the support. It's an honor and a pleasure for me to give this seminar talk here. So I present joint work with Vladimir Gerdt from Dubna, Russia. It's basically our contribution to this year's ISAC, which took place in Beijing in July. Our plan is to extend this a little bit further to a journal paper later on, and I'm presenting here the state it is in right now. So what is this about? Algorithmic approach to strong consistency analysis of finite difference approximations to PDE systems. The theme here is to go back and forth between differential polynomials and difference polynomials. So I will have three parts. Strong consistency of finite difference approximations, that's our motivation and the application. Then I show in the second part the Thomas decomposition method for nonlinear PDE systems. That's kind of on the differential side of the story. We have been working on that for a few years now. And this is well understood. One of the contributions, or the main contribution of this paper is that we develop a similar, but not quite the same, decomposition method for nonlinear difference system, and that's kind of on the difference side of the story. Difference in the sense that the quality of the output systems is not quite the same. I will comment on that compared to the differential case, but this is kind of where we can have maybe further work, and we shall try to extend it. I shall comment on this. Okay. So strong consistency, finite difference approximation. So the situation usually is the following. What people have been doing for a long time is to approximate a given PDE system. So you want to solve this PDE system, it's difficult. So what you do is to approximate this PDE system by a different scheme, a difference system. So instead of your given differential polynomials, if I use the mouse here, so you have basically given differential polynomials in certain number of unknown functions. U1 up to UM can be any number. This is your PDE system you are actually interested in, but then since it's difficult to solve, you maybe come up with a difference system which approximates it. So you have difference polynomials. Similarly, our convention in this paper is we use a tilde on top of all the notation if it's in the difference world. Okay, so tilde is for difference, indeterminate, difference polynomial, etc. So how is this approximation done? We have a grid in the space on which the function is defined. So we shall concentrate on the values of the unknown function only at the grid points. The grid points only, and for simplicity we choose here a Cartesian grid. Uniform step size, h is a positive number, and in each direction you kind of go with the same step size h for simplicity. This is for our paper for simplicity. And typically what you deal with is such a correspondence here, so this relationship. So I wrote on an example. First order partial derivative can be approximated by this. It's called the central difference, right? So you take grid points, like two neighboring grid points around the point where you're actually interested in the value, divide by 2h, this gives you a second order approximation. I guess everyone has studied this probably. The way you confirm this is you use the Taylor expansion, obviously. So here you have your approximate function, you use the Taylor expansion around the point in the middle. And this expression here, this difference expression, is cooked up in such a way that the zero order terms cancel, right? And then the first order terms with the first derivatives, if you expand this, right, in Taylor expansion, the first order terms cancel as well, and this makes this central difference second order approximation to this derivative, right? So another way to think about this, you could also multiply through by h if you like. You substitute in here the Taylor expansions around the grid point x1, which is written above. And then due to this cancellation, this expression here is the lowest, I mean the coefficient of the lowest power of h when you simplify this expansion, okay? So tail expansion here and there, some cancellation, and you have powers of h. If you collect powers of h, the coefficient of the lowest power of h is what we call here the continuous limit.
Excuse me.
Yeah.
Is the kj on the grid the same as the kj in the formula?
So you see, for the central difference here, you go one step in j direction, it's the j derivative, right?
Oh.
Here you go minus one step in the same j direction, and that's why you approximate here the j derivative. So this evaluates to second order the partial derivative in xj direction at the middle. I mean, middle in that sense, middle grid point, right? Does this make sense? So this is. I could have maybe also written down like just a forward difference, which makes just one step. So then you have a first order approximation, just Taylor's formula. But if you combine forward and backward difference, and you subtract them like this, the first order terms cancel, and you get in h, and you get a second order. Okay.
Sorry, just another question about notation.
Sure.
So the U1 through UM, those are distinct variables?
Yes.
Okay.
Yeah. So the u's are the unknown functions, can be any number. Here alpha is between 1 and m, and the setting allows arbitrary number of derivatives in differential algebra. So I come back.
So this is just the first order.
Yeah, this is just an example. Yeah, just an example. You can. So the point is, our work here doesn't address the question how to come up with this, because you have infinitely many ways of approximating a given derivative by such difference expressions. This is the difference quotient, right? As h tends to 0, you get this in the limit. We are not saying anything about how to come up with this, but our paper says the following. Given such a choice of how you approximate your derivatives in your PDE system, you come up with a different scheme. This is a system of difference equations. We propose a method how to judge the quality of that. So it's about consistency. I come back to that in a second.
And just to be clear, you're not worrying about any kind of boundary conditions?
Not at this stage,
Okay.
no.
Okay, so it's entire plane.
Yeah. Okay, maybe I should say this now. So obviously there's the notion of well-posed problem. So you would like to have a existence of a solution to a PDE system, uniqueness and continuous dependence on the data. So here we just look at consistency of the system, which means as h tends to 0, the different system should, usually this is studied just for one equation, right? In the textbooks you have one equation. As h tends to 0, you should recover or get back the original PDE equation, the differential equation. That's what consistency is, which basically means through the approximation, you study the right PDE, right? Your difference equation is not in the limit like a different differential equation, but the one you want to study. Convergence is a different matter. So if you solve the difference system and then let h tends to go to 0, it might not converge to an actual solution of the differential equation. So this is another matter which we don't address. So for us, this is a much more basic property that we study, is the consistency. So what I just described, we refer to as weak consistency. So usually in textbooks it's studied for just a single equation. And what we propose, even for systems of PDEs and then correspondingly systems of difference equations, is the following. First notation, we write this little triangle here. If the differential polynomial f is the continuous limit in that sense, I just explained before, or here it's written again, the continuous limit of the difference polynomial. So each difference polynomial in the u tilde 1 to u tilde m, right? For each such polynomial, I can do the procedure here. Let's substitute in the Taylor expansion for these different expressions around the same grid point, simplify and look at the coefficient of the lowest power of h. So that's the continuous limit. So this is what I've written here. So after Taylor expansion, right, around your grid point, you collect the powers of h, and this f of u here is the continuous limit. Okay, given this notation, what we propose is the notion of strong consistency is the following.
And what is du?
How is it quantified?
Quantified.
D. Quantify. What's the quantifier for D?
This just says, do what I just said, do the Taylor expansion, do simplification. So certain terms will cancel, hopefully, otherwise it's not very interesting. Like here before, I got this central difference, and this is made up in such a way that the zero order and the first order terms cancel, so you end up with h power of 2. That makes it second order. The coefficient of h to the power of 2.
So d is 1 here, by cross multiplying h.
Yes. So the d is depends on your given expression. So what order it is. So after cancellation, you look at the lowest.
So there exists
lowest d.
So you're saying there exists a d.
Yes.
It's not for all d's. There exists a d.
No, yeah. So you expand this expression. It will have a unique way of writing it as a sum of powers of h. This is unique, and so the lowest power is also unique. So d is just the lowest power of h that appears in this expansion. So you have higher order terms, but the lowest one is h to the d. So it's uniquely determined by what you start with. Okay, so this is what we proposed earlier, Vladimir, Gerdt, and myself, in earlier work. Is the notion of strong consistency. So you have your PD system F, capital F, differential polynomials. You have come up in some way with an approximation which is difference polynomials F tilde, and this should be the nice situation. For every difference polynomial which is in the perfect perfect difference ideal generated by your difference polynomials, there should be a differential polynomial in the radical differential ideal of the differential polynomials, such that this differential polynomial is the continuous limit of the difference polynomial you started with. Or said again in an alternative way, it would be the following. Every consequence of your difference system has as a continuous limit a consequence of the PD system that you're interested in.
Does F have to be unique here?
It will be, because the continuous limit is a procedure I just explained. You do the Taylor expansion, you collect powers of h, and the f of u is uniquely determined. The question is whether that's in the ideal, the radical differential ideal generated by the given PD system, whether it's a consequence or not. I will have an example on the next slide, so you will see.
Well, I mean, from the definition of the triangle there, it doesn't seem that you can solve f if you're given f tutor uniquely, because there are terms in the order hd plus 1 thing that involve f as well, right?
That might be, but...
I mean, you can ignore it, of course, then it's solved uniquely, but the equation doesn't say that it has to be unique.
No, so
it would be
again,
up to order.
Again, I see. Again, the right-hand side here is an expansion of whatever expression you have there, as in terms of powers of h. And then we don't mind the higher order terms, we just look at the lowest order.
So unique up to that order.
Yeah.
And the d would depend on the f tutor.
Absolutely.
Right. So they could change.
Yeah. That's what's your question about the quantifier, right?
Yeah, talking about other questions, a comment. So not everybody in the audience is familiar with perfect difference ideals.
I see.
Do you mind?
I have it on a later slide.
Oh, okay.
If that's okay.
That's great.
Okay.
And also a technical question.
Yeah.
So you seem to be dealing with sequences. So why perfect difference ideals rather than just difference ideals? No. Are you looking? So why are you looking for solutions of difference equations of fields rather than rings?
Well, that's a good question, and that's one of the directions which is kind of open now, because so we lack, or we are not aware of of a nice, let's say, Nullstellensatz for our situation. So the solutions, because you said sequences, the solutions we are interested in, I also have this on a later slide, are those U tilde functions on the grid which are restrictions of, let's say, smooth functions U. So every smooth, if you like, smooth function U or U1 up to UM without tilde can be restricted to the grid, right? Which gives you U tilde. Mm-hmm. So what we want to say here is the solutions we are interested in for the difference equations, not arbitrary sequences or so, but we are interested really because at the end of the day we want to solve the differential equations. We are interested in U tilde functions, so the functions which are candidates for solutions U tilde are those functions on the grid which arise as restrictions of smooth functions on the whole domain to the grid.
Yeah, then this makes sense.
Yeah, so again, this is one of the points we maybe can discuss later. We don't know a nice theory of like a Nullstellensatz also in this situation, but still looking at the perfect difference ideal. So what we are saying here is we have a set of difference polynomials, the left-hand sides of your equations, and you are interested in all the consequences somehow. So you can take sums of equations, differences, you can like linear combinations, and also if you have a perfect power of a polynomial, then the base of that power would also be a consequence, and then you can shift, because these are difference polynomials, so you also can shift back, right? So
one of the reasons for my comment was that because maybe checking is very complicated when you have perfect. So that's why. Yes. So I wanted to simplify.
Yes.
So
Yeah. We come back to that. We come back to that. Yeah.
This is one clarification. In the top of the slide, you're talking about a Cartesian grid.
Yeah.
But at the bottom, it doesn't seem that it depends on the particular grid.
No, as I said before,
you can still write down different formulas for, let's say, a triangular grid or hexagonal grid or something, right?
Yeah, hopefully, yes.
So as far as you're set up on the lower half of the slide, it doesn't matter. Is that correct?
That's correct.
Okay.
The interpretation later on is expected to be more complicated. You see, you have one of the main reasons we restrict here to the Cartesian grid here, as I wrote it down, you have the same step size h in each direction. Right. So you can have more interesting phenomena if you have different step sizes in different directions. Yeah. Then it matters. Well, the convergence matters how the pair, let's say you have two directions, h1, h2 right. step sizes, mm-hmm. how there might be interesting relationships between h1 and h2 as they tend to zero, right? What you get as a limit.
So that depends on the independence of the direction, you're saying, that's all, right?
Yeah. So.
Okay.
Yeah. Okay. So this is what I said earlier. Equation-wise, consistency we also call weak consistency, and this is usually what you find in the literature. The case of linear PDEs we have treated already in ISAC 2010, and there was no problem here for linear PDEs. Think of the operators which represent the given linear PDE. You can do Gertner basis, you can compute Janet basis or Gertner basis, both in the differential setting and the difference setting. And then what we proposed here is to compare this. This was our original approach just for linear PDEs, and then this work I'm presenting here is an extension to the nonlinear case. So what we proposed here, given a differential system which is linear, you compute, let's say, Janet basis or Gertner basis J1. For the given approximation, you have a different system, you do the same for the different system, you also have Gertner basis or Janet basis. And then you look at your Gertner basis or Janet basis for the different system, let h tend to 0, and see whether that will, in a limit, have the Gertner or Janet basis of the differential system as its limit. And if that is the case, so this is exactly what I said earlier, but restricted to linear differential. different polynomials.
And
Very go ahead.
so with this, did you try any no, real,
Examples?
Real examples people had, and whether you found something interesting, like there were some errors in the other people?
Yeah. So this will be in the next step on my slide. So you see this was 2010. In the meantime, Vladimir with other collaborators used that technique or this criterion and studied various approximations to well-known and well-studied differential equations. For example, here the 2D Navier-Stokes equations, they came up here in this paper, 2017 actually, came up with a new difference scheme which is strongly consistent in that sense, whereas others, earlier difference schemes were not, and they compared also numerically the outcome, and this behaved better. So here I reproduced the system, so you see it fits on one slide, but this is in the paper, okay?
So are you going to give us some necessary sufficient condition when the J2 would actually converge to J1?
Well, this is an algorithmic procedure, so we cannot predict when it happens other than doing the computation. So that's computer algebra. You would input your differential system, do what I said here, input your difference system, do the second step, and then the computation of the continuous limit on the previous slide with the little triangle, right? This is also implemented, so you can do the Taylor expansion by computer algebra, etc. And then this is algorithmic. But so you have to compute.
So that means that you have to compute both J2 and J1.
Yes, that's the procedure. Yeah.
And then verify that
it
converges.
Yeah.
Okay, thanks.
But this is kind of thing you would expect to do once, right? So because you would reuse the difference scheme, but you would test it like once for many years, and people can use it, right?
Yeah, absolutely. Yeah, of course. Yeah. This is in terms of looking at numerical investigations. What I'm talking about here in my whole talk is like a pre-processing. It's the algebraic approach is a pre-processing, and then if you sort it out, if that's strongly consistent or whatever, then you can do your numerical simulations. But
that's no proof that in any. Okay, never mind. Just in other words, for that particular equation you're computing, you can verify that it converges.
It's
All right.
for each PDE system and for each choice of approximation, it would be a new computation.
Right, and then you can't guarantee the other one unless you actually do the computation first.
The other one, you mean?
Well, I mean, let's say you choose a different step size.
I see. Yeah. Well. For what I said, the grid is fixed.
That, let's say, if the step size is within such a bound, then it will always converge. You can't prove it.
We don't say anything about conversions. It's just consistency.
I mean consistency.
Yeah.
I mean conversion. I mean in the sense of.
I see. Yeah. No.
Right.
So
you can't do that. You have to actually, for every different h, let's say, you have to actually.
So
show
H,
that.
it's still
You know
maybe
what
it's
I'm
important to make this clear that H is a symbol. So in the procedure I'm talking about, H is a symbol representing this positive number, but the limit, this continuous limit f of u is computed symbolically. So H is still a symbol. You do the Taylor approximation with H as a symbol, and then you read off the continuous limit as this coefficient of the lowest power of H. So that's
Okay.
I should have asked earlier kind of what the background is and where to start. So I noticed I should have maybe put more information on this.
It's okay. We don't hesitate to ask.
Please, absolutely. Yeah, please do so. That's fine. Yeah. Okay.
So this different scheme with this extra property. Do you know if they communicated to people who used different schemes with weaker properties, and if those people now use this one instead of theirs?
I think Vladimir has done that. At the moment, I cannot recall so much the progress in that direction. but he has been
There is some
touched.
effort to...
Yeah, absolutely. In the interest of time, I skip this, and here's a toy example, which is now nonlinear. So it's in the scope of the new paper. So you see u is squared, the unknown function. It's just one unknown function in this example. U is squared, so it's nonlinear, but this is kind of the simplest example I could come up with. So here I make a choice now how I approximate this. So I choose to approximate the first order derivative with respect to x by the forward difference, and the derivative with respect to y as well. Just the forward difference is one step, or going one step ahead, right? Then my resulting difference system looks like this. U tilde is now the difference indeterminate, and here I do the procedure, so to speak, by hand. We would have to check integrability conditions, so to speak, like in Grobner basis S polynomials, right? So here you would shift the first equation in y direction and shift the second equation in x direction in order then to take the difference of the two equations so that the most significant terms cancel and you get a consequence. This you want to reduce modulo the system, and you are interested in checking whether that normal form will be zero. I omitted the coefficients here in this line. You see sigma is the shift. So here is exactly your S polynomial, and after the reduction, you end up with this. You see the lowest power of h is 3, there's no more terms here, so this is equal, yeah? This is exactly the normal form in this reduction process, and the continuous limit is u to some power. U is the differential indeterminate, right? Which would be strongly consistent in our sense only if u equal to 0, the equation u equal to 0 was a consequence of the original system, but it's not. Of course, u equal to 0 is a special solution of that system, of course, but u equal to 0 is not a consequence. It's not the differential polynomial u is not in the radical differential ideal generated by the given equation. So this says my way of choosing an approximation, a finite difference scheme, let's say, but without boundary conditions in this case, choosing that to approximate the given PDE system is bad, so to speak. It's not strongly consistent, as I find the consequence in the difference system, whose continuous limit is not a consequence of the given PDE system. So here, curious modification. I stick to the forward difference in x direction and then choose the backwards shift, backward difference in y direction. I do the same or similar, analogous S polynomial, and I get 0.
It's supposed to be tilde, right? On top of uij.
No.
It's
no,
the continuous limit. So
Yeah, but then what's the meaning of ij?
I see. Yeah, I think I'm missing a tilde here. Yeah, you're right. Yeah. So if you expand this, you get this expression with your tilde, and the continuous limit will be u equal to 0 without the tilde. Yeah. Okay. That's the tilde.
Yeah, but then could you say how you concluded that it's not a consequence?
Okay. So the procedure, which I haven't mentioned here, which would do that in general, is the differential Thomas decomposition, which will be the second part of my talk. So for the differential Thomas decomposition, we'll take any such system of PDEs like here, nonlinear, and produces something like a Grobner or Janet basis, but this is now a tree of case distinctions in general. Each leaf of the tree will be something we call a simple differential system. So if I did it for this one, the tree would be just one leaf. There's no case distinction in that system. If I do the differential Thomas decomposition, it is already a simple system, if I see it correctly. And with simple differential systems, you can decide membership to the ideal it generates.
Could you try the computation, because you do the cross differentiation and then reduce?
Yeah. Okay. So so I need to kind of replan the order in which I tell things. So I'm happy to discuss the differential Thomas decomposition now. So it comes in several stages. So the differential Thomas decomposition has, so to speak, an algebraic part, which considers these kind of polynomials without knowing that these are unknown functions and their derivatives, so just algebraic equations. It does something to that, which I explain maybe in a minute because it's tangential to your question. There's a differential part to it, which checks the integrability conditions, like I did here for the difference case. So in that case here, what we need to check, differentiate the first equation with respect to y. You get partial uxy minus 2uy, all right? Second equation you need to differentiate with respect to x. You get the same by construction, the same by the intention, right? The same leading term uxy plus 2ux. You take the difference, and you should obtain, I guess, the difference is correct, a minus, if you look from above, minus 2ux minus, if I do this correctly in my head now, minus 2ux. You notice in that difference, which is a new differential polynomial you need to investigate, you have ux and uy appearing, but you can use, and you must use these equations here, which have leading terms ux and uy, in order to simplify.
So wouldn't you get u cubed?
Sorry, maybe we can do it. Partial x, isn't it? Minus u squared equals 0. Partial u by partial y, is it plus? U squared equals 0. So what I've done here is I differentiate the first one with respect to y. If you allow me to use English notations quicker, to uy, right? As a consequence, I differentiate it. Uxy, I differentiate this one with respect to x. I get plus 2ux. I take the difference. That was my intention. In order to do that, I get something new, which is minus 2uy minus 2ux, which can also be written as this is also equal to 0 as a consequence. Minus 2 times u times uy plus ux. Is that correct?
Yeah.
So now you use your original equation. Ux.
It cancels.
Oh, you can satisfied with this?
Yeah.
So it works, yeah. So
zero.
this turns out to be 0 if you use the original equation, so everybody is happy with that. This shows that the original system is already what we call passive, formally integrable. This is one ingredient of what we call Thomas decomposition. The algebraic part is fine, I haven't mentioned this yet, I can say this later. Differential part fine because I checked the cross derivative. There's no more to check in that direction. That makes this system simple. That's why what you would in general have a tree of case distinction in your differential Thomas decomposition. Here you start with a leaf already. There's no tree. So this is simple. So now in general, a simple differential system allows algorithmic test for membership to the radical differential ideal which is associated to it. So that's the one I'm talking about here. When I say all the consequences of that system, what I really mean is all the differential polynomials in the radical differential ideal generated by this one. The Thomas decomposition method, the similar kind of reduction like here, tells you a given differential polynomial, wherever it comes from, is in the radical differential ideal if and only if the remainder after division by those guys and all its derivatives gives you 0. And I've done this, so to speak, in this example. That was your original question. U equal to 0. I want to reduce it, but I cannot. Yeah? So I cannot use the given equations in my simple differential system to simplify u equal to 0, so that it's already in normal form. It's the remainder already of the division. It's not 0. So u as a differential polynomial is not in the radical differential ideal. So it's not a consequence of the given system. That's what I didn't spell out.
How to fix this?
Say again?
And then you propose how to fix this.
Yeah, so of course, I didn't change the original PDE system. It's still simple in the Thomas sense. Everything's fine. I just changed the approximation here. I happen to choose a different way of approximating the partial derivative with respect to y, namely by the backward difference. And then the analogous integrability check for the difference system gives me 0 here, whereas in the other case it didn't give 0, it gave something which was not a consequence. This.
Mm-hmm. And what if you just have a single PDE? Are there any general statements?
It simplifies, so to speak, to the textbook theory, in the sense that you do the then you just do the Taylor expansion, right? Like I did mention here. So you see that would be quite boring PDE, but if that's your equation, partial JQ equal to 0, yeah, then you come up with maybe this as an approximating difference polynomial. Of course, this is well known, and the answer is yes. It's strongly consistent because you can take the continuous limit of this one. It will be that. It's in these classical examples. It's of course done in such a way that it works, right? And yes, partial JU is a consequence of partial JU.
Do we need to have an irreducible polynomial for that?
Irreducible in the sense of algebra? Or?
Yes.
No. The differential Thomas decomposition.
So that you don't have to think. Like, if you're given just a single PDE,
yeah.
Is the answer always yes?
No, I'm not sure if I understand the question correctly. So you see, this is your given. If this was your given differential equation, it's maybe not very interesting, but let's say for simplicity, then somehow, of course, the answer depends on what you put in as an approximation here. So if I change minus to plus, it will no longer be correct, right? It will not have.
Okay.
Right? It's. Mm-hmm. And concerning irreducibility, I mean, the Thomas decomposition doesn't use necessarily factorizations. So you can use it in the Thomas decomposition to split your system up further. Yeah? So if your original PDE system has some equations in it which factorize, you can make use of that and have in your big tree, perhaps, right? Have another branch, and you split your given differential polynomial into factors. One factor equal to 0 in one branch of the tree, the other factor equal to 0 in the other. So you can do that, but it's not necessary. So it's up to you whether you want to split that up further or not. Other questions? Okay, so this was basically just a toy example to kind of give the idea what can happen in the simplest possible case, and you see, it's an interesting question. That's maybe fair to say. Okay, so now I think I can go quicker on the second part because I already revealed some of these contents.
We'll see.
I see. Okay. Okay. Yeah, please ask. I mean, it's a good discussion. Yeah. Please ask. So we have been working on this method. From the algorithmic point of view for a couple of years. The method goes back to an American mathematician, Joseph Miller Thomas, who developed this method in the 1930s. So the method is kind of related to also characteristic sets. Maybe most people in the audience know characteristic sets. So this is quite similar. The reduction process I mentioned is along the same lines, like also Rit was using, and so on. Before my talk, you mentioned Janet, so it comes in at this stage. Here's it's kind of the same context as I did on the board, right? So for two PDEs, or even more than two PDEs, you need to check their integrability conditions, so the cross derivatives and higher cross derivatives, etc., in order to end up eventually with what we call a simple differential system, which allows you to check membership. You need to take into account all these consequences before, right? And it's just to mention the Janet strategy. It works as follows. Let's say if you say X has priority over Y, this is an arbitrary choice now. Let's say X is kind of comes first, then you would say my derivative here. Maybe it's good to draw a picture. So you have your, in x and y, or let's say partial x and partial y, the points with integer coordinates in this orthant represent all the monomials in partial x and partial y, right? Commutative monomials. So Janet's idea is to decompose a given multiple closed set of monomials into cones. So in our example here, you have the leading term partial x squared in the second equation applied to u. There's only one unknown function here, and you have, this is this lattice point here, so to speak. And partial x partial y is here, partial x partial 1. And as you differentiate arbitrary order these equations, you will end up with leading terms which are all in this kind of sector or in this region, right? Every monomial in partial x partial y will appear as a leading term of a consequence of these equations if you differentiate sufficiently many times. And what Janet says, this is just a comment about the strategy. If, let's say, partial x has priority over partial y, let's say, then we decompose this region of monomials into disjoint cones by saying maybe partial x squared can be differentiated with respect to x and y. But partial x partial y, we don't allow partial differentiation with respect to x because it would interfere with my other cone. So that would be a one-dimensional cone here by this definition. Of course, you can exchange the roles of x and y and get a different picture, but this is one possibility. So the point in saying that is the strategy for checking all the integrability conditions in the Janet sense is to do the forbidden differentiation, you get a consequence here, and then do the reduction in the allowed way. This is the strategy. So we assign to each generator, this is an equation, the generator of the ideal, we assign to it what we call admissible derivations, non-admissible derivations, and the procedure of finding all the integrability conditions is to apply any non-admissible derivation. You get a consequence, reduce it in the allowed way, and this is what I did on the board, for example, or you can also do on this example. And this is a procedure which, in the linear case, this is a system of linear PDEs, ends up with what we call a Janet basis, okay, as opposed to a Grotner basis. So this is a little bit of a distinction. Okay, so this is the kind of the differential part. Okay, so just a setting. I mean, I think I don't have to say too much here. Differential polynomial ring is used. You have unknown functions and arbitrary numbers of the derivatives. They form the differential polynomials in this ring, which is known to be not Noetherian. That's why not every ideal in this differential polynomial ring is finitely generated. But the good news, as you all know, is that radical differential ideas in this polynomial ring are finitely generated, and that's what makes also the differential Thomas decomposition work in that sense. The membership I just talked about earlier, the membership is for this kind of ideals, not for arbitrary ideals, but for the radical ones. And these are the ones we are interested in. Remember the bottom line on my maybe second slide where I wrote down the condition for strong consistency with the double square brackets. It's that kind of ideal that we are interested in, and that's why this method is appropriate. Okay, so there's a reduction process involved, which I already mentioned earlier. Given a non-zero or non-constant, maybe differential polynomial, it will have an indeterminate such a uxy, etc., which represents the derivative, which is with respect to some chosen ranking the highest one. We call that the leader. It has maybe some power, and the coefficient of the highest power of that leader would be the initial, so the leading coefficient. So you can perform two kinds of reductions. Let's say you have two equations which start like this. The leader is the same, uxx1, which represents the derivative, but at this stage we might not care about this. then you perform the following manipulation. P and Q are given. You want to produce a remainder R. It's a pseudo reduction. You need to first multiply your P by some other differential polynomial in general, C, which by construction here is of course chosen to be the coefficient of that one, so that at the end the highest terms cancel. And you need to multiply Q by another uxxy to match with the third degree there, and then the difference will get rid of the highest term. Right? This is the algebraic reduction. There's no differentiation here. Similarly here, you might be in the situation you have two equations, one with leader uxxyy and one with leader uxxy. Then you need to, in order to find consequences of this, you do the same strategy. You do a multiplication where in the end some terms, the highest terms cancel. So you need to here differentiate Q with respect to y first. So then you have the same leader. Then you do the same thing as in the algebraic case. So this is the differential reduction. Now, this is kind of one basic step in this Thomas decomposition algorithm, where you would like, with your two equations, P is equal to 0, Q equal to 0, replace this pair by the pair Q equal to 0, R equal to 0. Yeah? You've just reduced P equal to 0 to something maybe hopefully simpler or smaller in some sense, which is R equal to 0, which is your remainder. Now, replacing the pair P equal to 0, Q equal to 0 by Q equal to 0 and R equal to 0 should not lose or gain any solutions. So it should be equivalent system. So this is true if we demand that C, the differential polynomial we multiply with here in this pseudo reduction, C should not vanish on the solutions. Otherwise you wouldn't be able to recover the P from the R. So that's basic observation. Similarly here, differential reduction, you differentiate first, same thing should be required here. The partial derivative of Q with respect to its highest derivative, which is called the separand, should not vanish on the solution set in order for the replacement of the pair P equal to 0, Q equal to 0 by the pair Q equal to 0, R equal to 0 to be an equivalence transformation. You should be able to come back from R equal to 0 to P equal to 0, and this is possible if you demand that the separand of Q doesn't vanish on the solution set. So what the Thomas algorithm then does is make case distinction according to whether an initial, which I should point to this one here, C is an initial, right, the leading coefficient of the highest power of the leader. C is it can be a differential polynomial in lower ranked variables, right? The distinguished case is whether that C vanishes on the solution set or not. So you will have a split in your tree, so to speak, of case distinctions. The algorithm will add as an equation C equal to 0 to your system. This is the case where C vanishes on the solutions. And C not equal to 0, you introduce an inequation in the other branch of the tree, and it will proceed further with all the methods I have been talking about in these two branches. So it might be that the assumption that C is equal to 0 later on turns out to be a contradiction, and then it will discover this, and the branch will lead to no output simple system. Okay, but in general you have these case distinctions. Similarly, the algorithm will make case distinction to check or to see the consequences of an assumption that the separand vanishes or does not vanish in a similar sense. Okay, reduction requires. So far so good with the Thomas decomposition method. So given a system of nonlinear PDEs, any number of equations, any order of the derivatives, any number of unknown functions, this reduction can be applied pairwise to equations. You can also input inequations in your system, and it naturally produces output systems which will have inequations due to these case distinctions. And apart from this algebraic manipulation and the integrability conditions in the Janet sense that I talked about earlier, this, let's say, roughly speaking, altogether gives you this Thomas decomposition method, the output of which is the following. We call it Thomas decomposition. Okay, so you might have started with a differential system S, like I just described. You perform this kind of algorithm, which I can go into more details if you like, and it produces some kind of tree of case distinctions. Some branches will lead to a simple system, as I will define next on the same slide, and other branches might lead into contradictions, then we'll omit it, right? And the leaves which survive in the tree, let's call the differential systems at these leaves S1 up to SR. They are each simple. I define this just in a second. And the nice property is that the solution set in analytic functions of the original differential system you started with coincides with the actually disjoint union of the solution sets of the differential systems at the leaves, the simple differential systems, which then allow checking membership, etc. And that's because of each time you branch, you have a new branch in your tree, you add an equation, C, let's say C equal to 0, C not equal to 0, and obviously this splits your solution set into two parts, right? And you don't lose any solutions, you don't gain any solutions. That's
good question.
Yeah.
When a Rosenfeld-Grobner algorithm splits into its own notion of simple systems, so that algorithm can test whether each component of the split is consistent or not. And that test is just purely algebraic.
Yes.
It's Grobner basis computation.
Yeah, simple.
But here, with these inequalities, can you still test for consistency, or there are some issues there?
Yeah. Each simple system has solutions. So you cannot have an inconsistent system as an output here. So I should say the inequations affect the solutions, obviously. So you rule out certain special solutions if there's an inequation like that. But the membership, I should say, the reduction process which decides the membership to the ideal, is not affected by the inequations. So the ideal. Maybe I should tell you what the ideal is we check membership to. Yeah. So
like maybe
just a second. Maybe it helps. It helps.
So you see here you do get irredundant decomposition, right? It's irredundant.
No.
Not necessarily.
There's no guarantee.
No. So this is related to what I just said before. If you take the inequation, it's already still here on the slide. If you take the inequations into account, you have solution sets which are disjoint. However, if you think along the lines of primary decomposition of the radical differential ideal, etc., as I said, the ideals are not affected by the inequations. You see, that's why I thought it might be good to show you the ideal that is actually check membership for. Okay, so if you have a simple system, we are in this situation, just one leaf of the tree. Yeah, let's say this is a simple differential system. What you look at is first step, the differential ideal, let's call it E in your differential polynomial ring, which is generated by the left-hand side of the equations, not equations only. Let's call Q the product of the initials and separants of these equations. They have certain leaders. Certainly they're constant, right? So they have leaders. They have a certain highest power in the leader. They have a coefficient of that, which is the initial. They have the separant. Each one of them has a separant, which is the derivative with respect to its highest derivative, right? And you multiply them all together, and you get your Q, which is a differential polynomial. Now, the ideal, which is in the center of this discussion, is this saturation ideal. So the differential ideal generated by the equations, the left-hand side of the equations, and we saturate by this product of initials and separants, which by definition means you are talking about this ideal which is consisting of all differential polynomials, R is the differential polynomial ring, for which there exists some power of Q. the factors of Q are the expressions which are not supposed to vanish on the solution set. So some power of Q multiplied by your candidate ideal element P is in E. So it's a two-step process. You take all the linear combinations of any derivatives of any P's, gives you E, and then take the initial separance into account, you saturate, you get this idea. It turns out, this is why this is a theorem, it turns out this ideal coincides with the vanishing ideal of the analytic solutions of the...
So you're saying that ideal saturated is radical?
Yes, as a consequence. It's if your system S is simple, this saturation is radical because it coincides with the vanishing ideal of your solution sets, which automatically is radical. Why do you say that? So there's no influence of inequations there. So if you call this like the Kolchin closure of...
Could you give me the definition of simple differential?
Yeah. I skipped this because...
So I guess, William, I guess your real question is how what's the condition on the QIs, right? So
on the what?
On the QIs.
On the QIs. Yeah, exactly.
Yeah, because otherwise you take QI to be equal to P.
Right, to one of the P's.
So it's somehow reduced, I suppose. So let's see. Let's see.
Yeah. So I skipped the reduced.
Okay, so
I skipped the definition because I wanted to show the idea first. But okay, sorry. So shall we look at the definition now?
Good.
So Thomas decomposition is such a collection of finitely many simple differential systems. Each of these systems has the following quality. We call it simple if the P's and the Q's, so there may be equations, this is the interesting case, there may be inequations or not, we don't mind, but all of them taken together will have necessarily, this is the definition, pairwise distinct leaders. So in that sense, it's what people also call triangular system.
Right.
So each equation or inequation, it doesn't matter for this discussion, will have there are no two equations or no two inequations and no pair of inequations or inequation which have the same leader.
Right.
Okay. The initial discriminants of Pi and Qj do not vanish.
Discriminants?
Yeah. So for the application
as a polynomial.
Yes, as a polynomial in the highest leader. So
in one variable. In the highest degree.
I should have said this already. You see, I wasn't sure what the background of the audience is, so I skipped some part. Different order of same thing. So we have the differential polynomial rings, these variables, and you choose a ranking. This is fundamental for the further discussion. So you fix your ranking.
Wait, we might never get to your main result. I try to accommodate this. I cannot tell what will happen next. But okay. So you have your ranking, and this determines in each non-constant differential polynomial the most significant variable. And along these lines, we consider each differential polynomial which is non-constant as a univariate polynomial in that leader, the coefficients of which are again differential polynomials which have their own leaders, which are ranked lower now, and they have their own coefficients which are again lower, etc. So it's a recursive representation, so to speak, of polynomial. I have a question about that. Would you go further?
Question about
Thomas.
Yeah. We were here in the definition. So the initial takes this recursive representation into account, the discriminant as well. The reason why this is significant is what we wanted to require and do require is that the separand of each equation doesn't vanish, you see if you take the resultant of a polynomial and its discriminant, you rule out, if that's different from zero, you rule out multiple solutions. So if the polynomial and the discriminant have a common solution, you have a multiple root. And this turns out to be matching with the separand condition. So the condition not vanishing separans is taken care of here by the non-vanishing of the discriminant.
Could you show that ideal?
Yeah, the one, yeah. So shall we just with that and then okay.
So that's
so passive.
the idea is radical then, because of the discriminant.
Because of,
Yes, yeah.
now to decide consistency of this, you will still run something like Rosenfeld-Grobner, right?
No.
Apply to E.
No. So
No Schoenstatt's, right?
So you see, there's the process here has different parts. There's, as I mentioned earlier, there's an algebraic part. There is a differential part, and these are combined. And so
you're claiming that consistency would be sufficient to do algebraically. Once you get into that.
No. So here I skipped this also in the interest of time. Here's just an algebraic equation. Okay, so you could think of P polynomial B. So the x here and the y could be a u and a uy or something like this. Right? But we don't care at this stage. It's just u is now a variable x. That's it. And this refers to a discussion of the Thomas decomposition method just algebraically. So let's say x has priority over y. Then x cubed is the leader. The idea here in the algebraic part of the Thomas decomposition is the following. If x has priority over y, what it means geometrically is we choose a projection of my solution, it's just real points of the curve, choose a projection onto the y-axis. You see y in the moment. So you see my points of the variety, I project them onto the y-axis. I now ask the following question. If I choose a point on the y-axis, how many solutions on the curve will there be with that value of y? So I'm interested in the project. This is a projection, and I'm interested in the fibers, the pre-image of the projection. And you see there are certain cases where the number of pre-images is 3 points here, and there are certain situations where the number of pre-images is just 2. And it could be still different from 2, but this is all there is in this example. The simplicity of a system in the algebraic sense, Thomas decomposition, means you have uniform behavior of the fibers under this projection. And not only here, I have only 2 variables x, y, you can have many variables. Remember, you have many derivatives of u. You do this recursively according to the recursive representation of polynomials. Leader and the coefficient has its own leader, etc. So in this sense, you have a sequence of projections of your variety onto the various lower and lower dimensional coordinate subspaces. And you require this condition in each step of this chain of projections. This is ensured by the algebraic part of the Thomas decomposition. Just take a differential polynomial, do this. So you do a case distinction. First obstruction to uniform behavior of the fibers would be there's a leading coefficient in front of x cubed, which could vanish. Then you get smaller degree. Doesn't happen in this example because the coefficient is 1, constant. Second obstruction would be the discriminant. That's why it comes into the definition. Discriminant is 0 for the yellow cases here. You want to rule out this as well. So you get these yellow solutions in a different branch of your tree. Just purely algebraically at that stage. Okay. Okay, so if we agree with that, algebraic part, if you just consider algebraic equations like this, I started with just one equation, you can have more than one polynomial equation, etc. The end result of the algebraic part of the Thomas decomposition method will be a splitting of the original algebraic system into simple, without the differential things, simple algebraic systems. It leaves off the preliminary tree, let's say, without having done any differentiation. Okay? And I say now why this discussion is relevant. Each of these simple algebraic systems is consistent. It will have a solution. So you have uniform behavior of the fibers under the projection. So if you start, you choose your value of y on the y-axis, any. And you know the fibers of the projection behave uniformly. There will be the same number of pre-images no matter which y value you choose. If you happen to have a green point on the y-axis, you will know there will be three values for x, which give you a solution of your system. This solution, or this solution, if you have chosen this value of y, right? If you happen to choose the value of y, which is the yellow one, there will be 2. And there might be other cases for other examples where you get 4 or 5 or whatever, but there will always be some. Okay? So the algebraic part takes care that each of the output systems, which are simple, will be consistent in that sense. So you start with any, you choose on the y-axis the smallest variable. There might be conditions on that as well, because there might be in the simple system, ultimately, there might be maybe, let's say, an inequation which says y not equal to 1000. And you must not choose y equal to 1000. That would be an inconsistent choice. But if you take all these conditions for the lowest variable, let's say y, into account, y must not be 1000, then the uniform behavior of the fibers tell you for your choice, you get 3 solutions for x, pair xy, which is on the curve, or in yellow cases you get 2. Okay. So now you do the differential part to all of this. So you have a splitting into algebraic systems, simple. You check the intermediate conditions and so on. And here the interpretation of the values you choose, like the value for y determines maybe a value of x. These are for the Taylor coefficients of an analytic solution. So to speak, the ranking, where was the ranking? On purpose is chosen in such a way that higher derivatives are ranked higher, right? So the lowest variable is u, always for ranking, which corresponds to the 0 order Taylor coefficient of your solution u to your differential system. If I can say in a minute more about this. So remember the picture with the curve. You choose your 0 order Taylor coefficient. Maybe, again, there are no boundary conditions. Boundary conditions might determine further restrictions on that choice. We don't look at this. Due to the algebraic part of the Thomas decomposition method, your choice of the 0 order Taylor coefficient, right, in your power series, it now depends on your choice which simple system you have to look at. Okay. But for each of these simple systems, it's built in that the fibers have uniform cardinality. So for your green simple system, if that's the one corresponding to your choice of 0 order Taylor coefficient for a solution, there will be exactly three extensions of your solutions as in the sequence of power Taylor's series coefficients. So if the next one depends on your ranking, if the next Taylor coefficient is the Taylor coefficient of x, first power, and then you have y, x squared, xy, y, and so on, right? Then the Taylor coefficient for x there will be 3 possibilities for that green simple system. So the reason why I say that is, at the end, you are sure each simple differential system will be consistent, because an analytic solution can be constructed in this way.
Okay. Yeah. And so given the time, would you mind explain the main results, and then when we can later on discuss
sure.
with the boards and details?
Yeah, sure. So the third part addresses the decomposition method for nonlinear difference system. So the way we obtain this is analogous to the Thomas decomposition, but since, as I said earlier, we are not aware of like a nice Nullstellensatz for our situation, difference equations, and the kind of solutions I talked about, restrictions of smooth functions to the grid, the quality of the output systems is not quite the same. So let's see. We have the notion that this may be a good slide to start with. We have now a difference decomposition. You see the similarity to the previous slide. we have now difference polynomials, difference equations, possibly also difference inequations. The procedure naturally introduces also inequations, but you can also start with inequations. Solutions in the sense I just said. We use a quasi-simple system. What is this supposed to mean? It will come in here. So again, it should be a triangular set. The equations and inequations have pairwise distinct leaders. Initials should not vanish for the same reason as before, but we don't insist now on the discriminants.
So you're talking about sum up behind your algorithm, right? But does your algorithm actually answer the question that you originally wrote? Can it test?
For the strong consistency, yes, but we don't claim, for example, that we can decide membership to a perfect closure. Okay, so here
can you at least test there is some implication at the very beginning, you said.
Yes, on the bottom line, yeah?
Yeah, on the bottom line?
Yeah.
Can you actually answer that question?
Yes, so the procedure will be as follows. You have your PDE system, you do differential Thomas decomposition as I just outlined. Mm-hmm. There can be many simple differential systems. You choose one simple differential system that contains a solution that you're interested in. Okay. So for this system you discretize, so which means choose an approximation in the original sense. And you wonder whether that's strongly consistent. We apply the difference decomposition technique to it, and that might split further up. Mm-hmm. But we then look at the continuous limit. So this is a procedure. So for each difference polynomial, you have this continuous limit, the coefficient of the lowest power of h, and this gives you a differential polynomial. As a continuous limit, it's a differential polynomial, and for the differential, simple differential system you started initially, the one you chose, you can now reduce check membership of this continuous limit, which is a differential polynomial, to the radical differential ideal of that simple differential system. And if this fails to be a member, we don't have strong consistency. If it is zero all the time, we have strong consistency.
But again, so you have an algorithm that answers the implication, right?
Yes.
Yes. Yes, correct?
Yes.
It's just you cannot test whether could you show that implication maybe everybody?
Yeah, we are not claiming that we can decide membership to the perfect ideal.
So
yeah.
Let's see the implication.
Yeah.
Okay. Yeah.
Yeah. So the condition again is for all. So the continuous limit must always be a consequence of your differential system, which you can check with the reduction of the differential Thomas decomposition.
So this whole formula you can check.
Yes.
You just don't know how to check pieces of the formula.
Pieces.
Like f belongs to.
Yeah, correct.
But you can check whether the whole thing is true.
Yes. Yeah.
Okay. So you actually answered the main question.
Yeah.
And the other question is just some technical question.
Okay. Yeah. Okay. Yeah.
So you're saying that if J2 in the limit x equals to 0 is J1, then this would be satisfied, right?
Yes, this is, at least the notation you used in your question is coming from the linear case, but it's similarly for the nonlinear case you would have similar. So of course this is a bit sloppy notation here. So as h tends to 0, it must not be like exactly J1, but it can be equivalent, right? So up to reduction.
Up to the
yeah. So it's a bit sloppy, this arrow word.
And do you have software that does this?
We have no finished implementation of this difference decomposition technique. I mean, I've done some experiments, but it's very slow. So it's difficult. But yeah, of course we want to have that. Yeah.
So do you have any idea of how many leaves of simple systems you have? Let's say for some standard kind of equation like Navier-Stokes.
Of course, for each concrete system, we can use the computer to check it, and then for Navier-Stokes the answer would be 1 because it's up to. You see, I can show you even the example, but in general, without you telling me what the system is, I wouldn't be able to predict it at this stage.
No bounds given.
I don't know of any. So just as an illustration, Navier-Stokes, if you're interested, would be in 3D would be like 3 equations and 4 equations. So describing how velocities and pressure in your fluid behave over time and in space. And the Thomas decomposition, if applied with the correct ranking, would reveal a famous consequence, the Poisson pressure equation. So up to this integrability condition, this is already simple. So if that's your ranking that you are interested in, then you would include this in your system, and you got your simple differential system already. It's just an example.
More questions?
I guess I will be around in the afternoon.
Yeah, let's talk in the afternoon in more detail maybe on the board.
Yeah.
Okay, thank you.